vector space. So we're going to define vector space as a set of all possible vectors of a given number of elements. But knowing that they are vectors, we already know that the set will be closed under the basic operations of the vectors like scalar multiplication and addition, and of course linear combinations also. And the vector space should support all the operations that are specified. So let me give you some examples. Let's take R2, a normal xy plane that you might have seen. Every point here has a coordinate, it's a pair of coordinates. And if you think of the coordinates as a vector, it satisfies all the conditions. And this coordinate space is actually a vector space too. But there is a distinction between the coordinate space and the vector space, because vector space, remember, is actually just a set of all possible vectors, while the coordinate space is a space in which you have points and shapes and curves. And so there is a slight subtle distinction. Now, if I take matrices of the same size, m by n, you can add them, you get another matrix of the same size. You can scale one, you get another matrix of the same size. So it satisfies all the properties. So that set also is a vector space because it's a set, it's a closed set, and the operations are defined. Similarly, complex numbers are a vector space also, very similar to R2. And if you have real functions, if you have functions of the kind f1 of x, let's say a single variable, and this is defined between 0 and 1. So I have some shape and some other function f2, some other shape, all defined within that. And then if I add f1 plus f2, that is going to be a function also, call it g. If I scale f1, I get another function, call it h. They're all functions. So it has the operations and it satisfies the conditions too. Space of functions also is a vector space because it has the basic operations and it satisfies all the conditions. It's just that if you look at the number of points you have between 0 and 1, you have an infinity of them. So it's like an infinite dimensional space. So it's something like, I shouldn't call it R, but let me call it R anyway. So something like R infinity. Okay, so it's a space of functions. This kind of thinking of a space of functions as a vector space is the basis of Fourier transform. There we will be defining a bunch of vectors that are functions as the foundational basis vectors, and then everything else can be expressed in terms of those. It is also the foundation of quantum mechanics. The linear algebra as it is used in quantum mechanics also uses the same idea, functions as vectors. Okay, you just have to define a dot product and then you can have orthogonal vectors, etc. So that is vector space, set of all possible vectors of a given number of components. A vector subspace is defined in terms of a vector space. It's a subset of the vector space in which the operations scalar multiplication and vector addition are closed. So if I were to give you an example, we had example 2, we had a subspace which was a line. If I take a vector here on this line, I scale it, what do I get? I get another vector on the same line. Suppose I have two vectors and I add them, I get some other vector that is on the same line. I can never get out of the line. All the vectors are on the same line, so it is closed under scaling and addition. So for that reason, this is a vector subspace, a line going through the origin. In example 3, we had two vectors of the kind that spanned the xy plane. So that also is a subspace. Let's start talking about the basis of a vector space or a vector subspace. So again, definition. As we saw, if you have a bunch of vectors, you can create their span. That will always turn out to be a subspace. And if you have enough of them, linearly independent ones of them, then you will have a vector space. The minimum set of vectors to span a space or a subspace is called its basis. So there are two requirements. They have to span the space or the subspace and they have to be linearly independent. So that's enough actually. If I say a bunch of vectors are linearly independent and they span the space, if they are linearly independent, then they will be the minimum set. So let's define it in a slightly different way. It's also the set of vectors which can form linear combinations to express any other vector in the space or a subspace, okay, as a finite linear combination. So what it means is that you need enough number of vectors to span, but not too many. So let's take maybe a couple of examples. In our first example, we had two vectors, x1 and x2. They were linearly independent, and we saw that their span was actually all of R2. So those are basis vectors for R2. You need both of them. One of them was not enough, and you don't need any more than two. If you had one more, you don't need it because these two already span all of R2. In fact, if you had one more, that would necessarily be a linear combination of these two. In the 7th example, we had x1 and x2 similar to the red and blue vectors here, except that I added a third component because they were in R3, and I added a purple vector which had a component only in the third direction. So these are also basis vectors for R3. Again, you need all three of them. Any two of them will give you only a plane, and you don't need any more, because if you add one more, that will necessarily be a linear combination of these three, because these three already span all vectors in R3. So counter example, in the second example, I had a subspace which was a line, had two vectors in it, x1 and x2, such that x2 was twice x1, and you don't need both of them. You need only one of them to span all of that line, because one vector will define a line, and then you just have to specify the length of that vector to give the position in that line. Okay, so if you had two, that is one too many. So for that subspace, which is a line, you need only one. And in the third example, we had two vectors in R3. That is not enough. You need one more vector, because these two would span only part of R3, which was the XY plane. Easy to see it when you see examples, but kind of hard to visualize or understand it maybe when I say these things in words. Dimension is actually the number of basis vectors needed to span the space or the subspace. So as you know, we defined the span as a span of a set of vectors, and the set had a cardinality, which is just the number of vectors in the set. So I can use fancier language here to say that the dimension of a vector space is the cardinality of any basis set. Now, you can have several different basis sets, because you can have different vectors, different basis vectors, basis sets really, but the number of basis vectors will be the same, and that is the dimension. And that property is immutable. Okay? For a given space or a subspace, there is only one dimension. By one dimension, I mean it's got only one number that represents the dimension of that space or subspace. For a vector space, the dimension happens to be the same as the number of components. So if I have R3, each vector will have 3 components. So the dimension of R3 is actually 3. But for a subspace in R3, that is not true, which is something we will have to see later. An example, Rn has a dimension of n, and that is the number of linearly independent vectors needed to span it. And x, a member of Rn, will mean that x has n elements. And if you are thinking of vector subspaces, a line through 0 has a dimension of 1, okay, in Rn. So the subspace has a dimension of 1 because you need only one basis vector for it, but it lives in Rn. So each vector in that subspace will have n components, but the dimension of that line is only 1. A plane has a dimension of 2 similarly. Space of functions, on the other hand, will have infinite dimensions. Now let's take one special set of basis vectors. That would be the identity basis or the coordinate basis. So identity matrix and the unit vectors will form a basis, and it's actually a very good, that's probably the best possible basis set that you can find. The columns of the identity matrices are unit vectors, and they specify the directions in the coordinate space. In R3, I have the 3x3 identity matrix like that, and if I take the first one, that is one vector, second vector, third vector, call them by some name that physicists are fond of, and then I can express any vector x, y, z as a linear combination of those 3 vectors, and this happens to be a very good basis because each of them, the length is 1, and they're all orthogonal to each other. So orthogonal basically means the dot product of any pair is 0 unless it is with itself, in which case it's going to be 1. So I dot j, 1 times 0, 0 times 1, 0 times 0, add them up, you get 0, and so on.